Look at the sheer scale of our sun. It swallows everything around it in violent rivers of plasma. And right on the edge of this inferno races a tiny, scarred world, moving faster than anything else in our cosmic neighborhood. For centuries, when humanity looked at the planet orbiting closest to this immense heat, we assumed it was completely dead, a silent gray rock baked by intense radiation. The assumption made perfect sense. Under direct sunlight, the ground here reaches nearly 430 degrees Celsius. That is hot enough to melt solid blocks of tin and lead. But hidden deep inside the permanently shadowed craters of this blazing world lies an unexpected discovery: millions of tons of frozen water. Understanding how ancient ice survives on a planet practically touching the sun requires looking past our basic assumptions. Mercury exists as a series of environmental contradictions that defy our standard models of planetary physics. Let's start with a common misconception. Despite being the closest planet to the star, Mercury is actually not the hottest planet in our solar system. Venus claims that title. This comparison diagram shows exactly why. On the left, Earth has a thick, continuous atmospheric boundary layer that traps and holds heat. On the right side, Mercury has almost nothing. Instead of a true atmosphere, it possesses an exosphere, a fragile, constantly disappearing veil of atoms, some thin, they rarely ever collide with one another. Now watch what happens when we shift this diagram to a thermal cross-section. Because there is no thick gas to insulate the planet, heat escapes into space almost immediately. The moment darkness falls, the temperature crashes by over 600 degrees, plunging to a bitter minus 180 degrees Celsius. Proximity to a star does not guarantee absolute continuous heat. Here, it guarantees an environment defined entirely by violent thermal whiplash. The extremes do not stop with temperature. Mercury travels at over 170,000 kilometers per hour, fast enough to circle Earth in under 15 minutes. Yet, while it races through space, the planet rotates on its own axis agonizingly slowly. To see how this affects time on the surface, look at this top-down schematic of the inner solar system. Mercury travels in a highly elliptical orbit, meaning its path is stretched into an oval shape rather than a perfect circle. If we shift this diagram down to a surface-level perspective, we can track the mechanical result of that stretched orbit. As the planet speeds up near the Sun, its orbital motion briefly overtakes its slow rotation. The Sun appears to rise, pause in the sky, move backward, and then reverse direction again to continue its climb. Because of this orbital distortion, a single solar day on Mercury, from one noon to the next, takes exactly 2 full Mercury years to complete. On this world, the traditional relationship between time, days, and years is broken. This ancient, heavily battered surface tells the story of a destructive past. Billions of years ago, massive asteroid impacts struck with so much force that the kinetic shockwaves traveled completely through the interior, shattering the landscape on the opposite side of the planet. And the destruction hasn't stopped. The planet is still physically shrinking today. As its interior cools down, the outer crust contracts, violently cracking and thrusting upward to form towering, jagged cliff faces that stretch for hundreds of kilometers. To understand why it's shrinking, we have to look inside. This 3D cross-section reveals an incredible structural anomaly. When we peel away the remarkably thin outer rocky shell, we find a disproportionately massive, glowing iron core that takes up nearly 85% of the planet's entire radius. Scientists are still debating how a rocky planet ends up with such an oversized metallic center. A massive ancient collision might have stripped away the outer rock, or the intense radiation of the newborn sun simply burned the lighter materials off before they could settle. What we do know is that deep inside this giant core, molten metal continues to move. This movement creates a dynamo effect, generating an active, surprisingly off-center magnetic field. Beneath the battered crust, a dynamic, active heart continues to generate power despite the constant onslaught of solar storms. Which brings us back to our initial paradox. How does a planet bathed in intense solar radiation hold on to millions of tons of frozen water? The mechanical solution is perfectly illustrated in this side profile diagram. Mercury has almost zero axial tilt, meaning it stands completely straight up relative to the sun. Notice how the incoming horizontal sun rays graze the surface, skipping entirely over the deep, recessed cavities at the poles. Inside these pitch-black craters, the temperature plunges to a permanent minus 170 degrees Celsius. When ancient water-rich comets crashed into Mercury during the early days of the solar system, their ice became trapped in these eternal shadows, preserved indefinitely. The planet's literal geometry, a lack of axial tilt combined with deep, lightless craters, preserves ancient water in plain sight, just millions of kilometers from the Sun. For centuries, our Earth-bound telescopes could only see a blurry, moving point of light. That limited perspective was finally left behind when NASA's Mariner 10 and later the Messenger spacecraft reached orbit and began recording. These missions systematically mapped a totally unknown world. They verified the shrinking crust, identified the vast deposits of polar ice, and analyzed chemical anomalies that continue to puzzle planetary geologists today. Today, we recognize Mercury for what it really is. It is a world actively losing its own atoms to the solar wind every single second, while simultaneously gripping the ancient, icy remnants of the early solar system. Mercury forces us to abandon our assumptions. It proves that the most extreme, unforgiving environments in the universe often hold the most complex and delicate secrets.
Please subscribe my channel for more informative video like this.